we have 0 times infinity, or infinity minus infinity. Okay. Now, these are not absolutes. It's not exactly 0. These are representing. 0 is representing a very small number. So if you have a very small number times a very large number, do you get 0, or do you get a large number, or do you get something in between? This does not equal 0 because infinity, remember, is just a very large number. And this is another very large number, not necessarily the same large number. So if, when we're evaluating a limit, I get either of these two cases, we are going to rewrite it so it is in the form 0 divided by 0, or infinity over infinity, and then we can use L'Hopital's rule. Let me show you an example of that. So again, if when you first plug in the numbers, you get 0 times infinity or infinity minus infinity, you're going to have to rewrite the function so that it's going to be a fraction. And when it's a fraction, you'll have one of these forms. So let's look at that example. So if we have the limit as x approaches infinity of x times e to the negative x. Well, if I plug that in, we have infinity times, well, e to the negative infinity is really 1 over e to the infinity. 1 divided by a really large number is 0. So we have our form infinity times 0. So we're going to try to rewrite this. And this one is a simple one to rewrite because we have a negative power. So we'll just rewrite it so it's a positive power. Now when I plug it in, I get infinity over e to the infinity, which is a really large number. Now we can do L'Hopital's rule. L'Hopital's rule says, take the derivative of the numerator and the derivative of the denominator. Now when I plug it in, I get 1 over some really large number, and that gets really small, so the limit is 0. There is a special case where we're going to need to rewrite it. Suppose we have this one. Suppose we have the limit as x approaches infinity of x times the sine of 1 over x. If I plug in infinity, then we have infinity times, well, the sine of 1 over infinity. 1 over infinity gets really small. The sine of 0 is 0. So we need to rewrite this so that it's a fraction. Nothing's raised to a negative power, but I could put this on the bottom by using some algebra skills. So if we have the sine of 1 over x divided by 1 over x, that's the same thing as x times, because when we divide by a fraction, we're really multiplying by its reciprocal. Now, if I plug in infinity, I have sine of 1 over infinity, which is 0. Sine of 0 is 0. 1 divided by infinity goes to 0. Now I can use L'Hopital's rule. So the limit, x approaches infinity, I need the derivative of the numerator. Well, the derivative of sine is cosine of that same angle times the derivative of that angle. The derivative of 1 over x is negative 1 over x squared. Now I need to take the derivative of the denominator, which is negative 1 over x squared. These can reduce, and so now I'm left with the cosine of 1 over infinity, which is really the cosine of 0, which is 1. So in this case, we found that the limit when we had infinity times 0 was 1. In this case, it was 0. There is a third case, and these are all listed on the worksheet on the website. The third case is, what if we end up, when we plug in our limits, with something like 1 to the infinity, or infinity to the 0, or 0 to the 0. Again, these representing not zeros and not ones, but numbers really close to 1 that get really large. Really large numbers raised to a really small power. Really small numbers raised to a really small power. So if we have those, what we're going to have to do is take the natural log of both sides and then evaluate from there. So let's look at an example of that, where we need to take the natural log of both sides. Here's a fun one. The limit as x approaches 0, no, infinity, sorry, can't read my writing, of 1 plus 1 over x to the x. Now, if I plug in infinity, 1 over a big number is 0. So it's really like I'm taking something close to 1 to a really large power. That's my case. So I'm going to set this limit equal to y. Now I'm going to take the natural log of both sides. So if I take the natural log of this side, I can move the limit in or keep it out. So x minus, as x approaches infinity, the natural log of 1 plus 1 over x to the x equals the natural log of y. Now my properties of logarithms say I can bring this x out in front. So that becomes the limit as x approaches infinity of x times the natural log of 1 plus 1 over x equals the natural log of y. Now, I want you to plug in infinity. What do we get? I forgot to write it, I'm sorry. Up here, we got 1 to the infinity. So we knew we needed to take the natural log of both sides. Now that I've done that, now if I plug in infinity, I get infinity times the natural log of 1 plus 0. So the natural log of 1 is 0. Well, if we get infinity times 0, we need to rewrite this as a quotient. So, again, nothing's raised to a negative power, so I can move that x to the denominator. So we have the natural log of 1 plus 1 over x divided by 1 over x equals the natural log of y. Now when I plug in infinity, I get the natural log of 1, which is 0, over 1 over infinity, which is 0. Now we can do L'Hopital's rule. All comes back. So I'm going to take the derivative of the numerator. The derivative of a natural log function is 1 over this quantity times the derivative of this quantity, which is negative 1 over x squared, divided by the derivative of the bottom, which is negative 1 over x squared, equals the natural log of y. Again, these reduce, and we're left with the limit as x approaches infinity of 1 divided by 1 plus 1 over x equals the natural log of y. Now when we plug in infinity, we get 1 plus 0, so this limit is 1. That equals the natural log of y. How do we solve that equation for y? Just rewrite it in exponential form. E to the 1 equals y. So my limit over here is equal to e. The limit as x approaches infinity of 1 plus 1 over x to the x equals e. You may remember that from pre-calculus when you did compound interest. Those are the three forms.